Okay, well, here's what we had last time. A big theorem. The big theorem is that a bounded monotonic sequence converges. And it's another one of these cases where mathematical language is very, very efficient. There's just 5 words here. One of them is the letter A. We don't care about that. Bounded monotonic sequence converges. A whole lot of ideas are being conveyed with very, very short phrases, excuse me, and ideas. So let's go over what these are again. So a set of real numbers is bounded if it's contained in some finite interval. Okay? There's no need to be efficient with a thing like this. So just as an example, we're going to think about this. We're going to say, think about the set one over n, where here's what n is. It's 1, 2, 3, 4, ... Okay, so what is this? This is the collection. Well, when n is 1, it's 1, 1/2, 1/3, 1/4. You get the idea? And if you think on a number line, an approximately horizontal number line, here's what you have. There's the number 0. How about these guys are in blue? There's 1. There's 1/2. There's 1/3. There's 1/4. And you see I'm going to run out of stuff right here. I can't keep writing it forever, but that's what that is. Okay, the first thing is, just observe this is contained in the interval from minus 10,000 to 10,000. So it's bounded. Now, what you might think when you look at that is that was tremendously wasteful. Why would I pick the interval from minus 10,000 to 10,000 to bound such a simple set? Because it's not like they were going to charge me for the endpoints, right? It doesn't really matter. There was no need to be efficient. This theorem that's up here doesn't say a bounded monotonic sequence converges provided you can bound it as efficiently as possible. It doesn't care. It just cares that it's bounded. Okay? The efficiency thing is actually secretly built into it, and it's sort of user transparent. You don't need to find it. Okay? We could bound this set more efficiently. E.g., how about using the interval from 0 to 1? But there's no need if all we need to do, if all we want is to show the set is bounded. So the fact that I talked about last time I saw you, which I guess was Tuesday, a set of real numbers that is bounded above, let's say, has a least upper bound. Okay. What is a least upper bound? Well, it's the smallest upper bound possible. So you have to parse this carefully. This is the smallest number with the property that it's bigger than every number in the set. Okay, so let's look at a little example. Let's modify this one up there. I'm going to think about this set. This is going to be 1 minus 1 over n. And again, I'm going to have n go 1, 2, 3, 4. Okay? Right, well, this set's going to be bounded. But here's what this is, right? When n is 1, you get 0. When n is 2, you get 1/2. When n is 3, you get 2/3. When n is 4, you get 3/4. If it was 5, you'd get 4/5, right? Get the idea? Okay, so obviously this set is bounded above. And the reason is, well, everything in here is going to be less than 10, for example. Okay? But you might ask yourself, what is the least upper bound for this set? Well, and hopefully I can convince you, maybe with a little number line argument. Again, so we're starting out here at 0. And then what are we doing? We're going to do 1/2, 2/3, 3/4, 4/5. I'm running out of room. But you can stare at this thing, make n as big as you want. You start to subtract a teeny tiny number from 1. And so what you'd kind of guess here is that the number 1 would be the least upper bound. This number 10 was way out here, right? Okay. 1 is an upper bound, and it's smaller than any other upper bound. If you had an upper bound that was less than 1, well, then the fact is, if you picked n large enough, you'd get an entry that was bigger than it. It wouldn't work, okay? So a reasonable question how does one determine the least upper bound of a given bounded? And the answer is very difficult in general. I don't know. That could be very, very tricky to do. Fortunately, and the wonder of this theorem up here, and that's my whole discussion about efficiency, we don't care. As long as we know the set's bounded above, we know it has a least upper bound. As long as we know the set is bounded below, it correspondingly has a greatest lower bound, which is what you'd get if you turn this whole thing 180 degrees. So as long as a set is bounded, it has most efficient bounds, namely the least upper bound and the greatest lower bound. There's no need to find them. Okay, so if you look at the number line here and you tell me, okay, here's this set, call that set A or something, right? And you say, okay, I know that there's an upper bound up here, there's a lower bound here, because I know A is trapped in some interval. Let's say minus m to m. That's m. This is minus m, let's say. Okay, then you're guaranteed there must exist a least upper bound. That's an upper bound that is smaller than every other upper bound, and a greatest lower bound. That's a lower bound that's bigger than every other lower bound. Okay? So, and the point of the theorem a non-decreasing sequence that's bounded above converges to its least upper bound. A non-increasing sequence that's bounded below converges to its greatest lower bound. In practice, to use this theorem, given a sequence, find any bound whatsoever, however you spell that, then show the sequence is non-decreasing or non-increasing, and this is the key thing, once n is sufficiently large. If you can do those two things, you win. Okay, so let's look at this example. I mean, this is brain dead simple, but it's just the idea. See, I would not even bother computing any kind of limit for this. There's my sequence, okay? AN is bounded since it's contained in minus 10,000 to 10,000. And yeah, I know, I could have done a lot better than this, but they're not paying me for that, okay? Now check this out. If you write this function, what's the derivative of this? It's 1 over x squared, isn't it? Which is bigger than 0 if x is bigger than 0. So look at what I did. I said, you know what? If you think about this function here, its derivative is positive. And what that means is that f of x is an increasing function which means that an plus 1 is bigger than or equal to an for all n. Okay, the conclusion is an converges. It's non-decreasing, and it's bounded. That's it. Okay? Okay, let me give one more quick example. This is going to be a short lecture because the internet connection here is absolutely terrible, and this is hard enough for you to think about, so you should spend some time thinking just about this problem. Let's go try to find a better example of this. All right, so here's a cool example. We're going to make an equal to n cubed over n to the fourth plus 10,000. I'm going to give you a little work to do. I want you to, number one, I want you to show this sequence is bounded. Okay, that's not hard to do, of course, because you've got n cubed divided by n to the fourth, and you kind of know what's going to happen here, right? As n gets bigger, this is basically going to act like 1 over n. Okay? The second thing is show it's increasing until n is about equal to 13. I think that's what I want. I think this is what I want this one to do. Sorry, I'm looking at my phone and looking at the computer at the same time. Yeah, good. Okay, show it's increasing till n's about 13, and then decreasing after that. Okay, so the conclusion should be that an is non-increasing once n is bigger than 13. It's bounded, so it converges. Okay, so how are we going to show it's bounded? I mean, let me give you a little idea of that. Why would it be bounded? Well, n cubed is less than n to the fourth if n is bigger than or equal to 1, isn't it? So n cubed is going to be less than n to the fourth plus 10,000. This magic number 10,000 is always here. Again, if n is bigger than or equal to 1. So n cubed divided by n to the fourth plus 10,000, well, that's less than 1. So it's definitely bounded above. And then the other point, I guess I should have just done this for you. I mean, look, that's bigger than 0, that's bigger than 0, that's bigger than 0. So the whole point is that sequence is trapped in the interval from 0 to 1. Now, I don't know what the least upper bound is. Maybe it's 1. Kind of seems like it should be, but I can't tell. I don't care. All I care is that it's bounded above, and that it's bounded below. So I'm going to go ahead and you're going to go ahead and do number 2. So here's the thing for you to do at home. Use some calculus to show part 2. Okay? And I will leave you there. I'll send you something else tomorrow.